thank you for waiting for the last talk of the whole conference. Nati will talk about geodesic geometry on this. Please.
Okay, thank you. I'm glad to be part of this. I don't know what this is called, a birthday party, but at any event, I'm happy to be part of this. So I'm going to speak about several aspects of how to think about graphs in geometric terms. Many things exist. I just want to mention, for example, there is a beautiful book by Laszlo Novas, which came out about 2 years ago, which covers many such connections. But it's really, even this beautiful book doesn't cover even a half of what's there, and not even a tenth of what should be there. So I'm encouraging you to look into this. So the basic principle behind what I'm going to tell you today is essentially everything that you know in geometry. It's a good idea to look it up also in the discrete world. And perhaps you have a sense of what geodesic geometry is on surfaces, on manifolds, and so on and so forth. But you're not going to need it. It's just, as an inspiration. So let me start. Oops. What's happening? Oh, okay, good. The first reference to geodesic geometry and graphs goes a very long time back in history. There was a Danish mathematician, very influential in both graph theory and group theory. And he wrote one of the earliest books in graph theory. And he came up with the following definition. By the way, you see everything good, you listen, you're hearing me good? Yeah, we're good?
Yes. Okay.
Okay, excellent. Just checking. Okay, so he defined a graph to be geodetic if for every two vertices there is a unique shortest path that connects them. So let's talk about this for a moment. Do we know such examples? Well, some examples exist just trivially. By the way, another thing, did you see my cursor on the board? If I use?
Yes.
Okay, excellent. So for example, things like trees, obviously are geodetic because there is only one path between any two vertices. So complete graphs, the same thing. The odd cycles is already a bit more interesting. And this is the most interesting example on this slide, the Petersen graph. The Petersen graph, which we're going to encounter again in a few slides, is a very interesting and very strange graph. It has diameter 2 and girth 5, which means every two vertices either are neighbors. If they're not neighbors, they are connected by a unique path of length 2. For example, you want to go from here to here, there is a unique two-step path connecting you, and that's it. So in fact, along what I told you that it is geodetic. And all I asked, can we characterize them? And then the situation is still very, very bad. We are very far from characterization of this. And somehow this question was almost forgotten. I've been in this area for many, many years, and I found out about Ore's work only a few years ago. I think it's a fascinating question, and I'll add a question of my own soon about this. So here's a conjecture that I made just recently. So first of all, when you start thinking about geodetic graphs, we said that trees are obviously geodetic, but that's uninteresting. So it's something that there is really no loss of generality if you say that you consider only two connected graphs. If it's not, then you just glue them together. It's really uninteresting. And there's another more meaningful restriction. Perhaps you want to forbid vertices of degree 1 and 2. Why? With the vertices of degree 2, this means that certain edges you can think of it as a graph in which edges have integer length. And then the question becomes more arithmetic in nature. So I really want to concentrate just on geometry and combinatorics. So I want to forbid it. So I'm restricting myself now for the discussion to geodetic graphs in which all the vertices have degree 3 and above. And I'm conjecturing that the diameter of such graphs is bounded by an absolute constant. The best result in this respect is the diameter of 5, which is the flag graph of finite affine planes, whatever that means. So at the moment, for all we know, maybe the absolute constant may be 5. We don't know. But this is just, this was intended just as a way to get into the subject. And now let's start talking about, so everything that I tell you today is joint work with my PhD student, Daniel Cizman. And we introduced this notion of, you'll see, there are several new notions. But let's remain for a moment with a geodetic graph the way that Ore defined them. So what is the situation there? If you consider the collection of all geodesic graphs in the geodetic graph G, then what do you have? For every 2 vertices, there is a unique path, UNV. There is a unique path that connects them. We call this PUV. And it has the property that a subpath of the path in the collection is also, so in other words, if the chosen path from UNV goes via X and Y, then the subpath connecting X and Y is PXY. In this property, this is going to be the main thing of what we're going to discuss today. Such a path system is said to be consistent. And this is what we would like to understand. Our goal is to understand consistent path systems. By the way, let me just say that please don't hesitate. If you have questions or comments or anything, don't wait till the end. Ask as we go. Now, actually, the story is much bigger, and there is, if you start thinking about these things, you realize how little we know. You see, it's very easy to turn a graph into a metric space. Even if you do nothing, you just take, you ask what is the least number of hops to go from X to Y, that's a metric. But you can do, many more, there is a much richer set of options for you. You can assign length, positive length to the edges, and now it doesn't only count the number of hops, you add the length of the edges that you traverse, and that makes the graph into a metric space. There are many different ways of doing this, and even this is something that we are far from understanding. So, for example, you can bunch them together, 2 sets of weights. You put them in the same class if the derived geodesic path are identical. We don't understand this. This is still, I think, a very interesting subject for further research, but we're not going to talk about this too much today. So, but if you have such a set of weights and you consider the shortest path, then this gives you, obviously, a consistent path system. And so somehow this is the obvious way to come up with a consistent path system. You assign positive weights and you say, take the shortest path. You may ask, what do we do if coming back perhaps to Ore, if there is more than one way to get with the same distance? Well, you can either you choose the edge length in a generic way, or it's very easy to break ties. I don't want to go into this. This is very simple. So this will not concern us too much. For example, this is, you can, to begin with, pick some ordering on the edges and then do the preference according to lexicographic ordering, something like this. Okay, so now we come to the most basic definition and concept that we're going to be discussing today. I give you, so please make sure you understand this definition, because this is what we're going to be talking about throughout my talk. Let me also say, here it's already a long meeting, and that's the last one. I'm only going to give you really one and a half proof. It's not going to be, I think, I hope, not too demanding, okay? Mostly I'll try to give you a sense of what these things look like. Okay, so we have a consistent path system. I have a simple undirected graph, and there is a consistent path system. Again, what does it mean? For every two vertices, there is a path, a chosen path that connects them. And if the path from U, the chosen path from U to V goes via X, then it's the concatenation of the UX path with the XV path. Question, does such a consistent path system necessarily come from weights on the edges? So I already tell you the answer is no, you will see. And so certain graphs, the answer can be positive. Every consistent path system is what we call metrizable, and certain are not. And a graph in which all the consistent path systems come from edge length is going to be called metrizable. So this is the main object of my lecture. We want to understand what metrizable graphs look like, or we want to understand this property of metrizability. So first of all, here is a first example, a graph, a non-metrizable graph. And the non-metrizable graph, we already saw it, is the Peterson graph. So let's come back and understand what this path system, the chosen path system is. As I mentioned before, in the Peterson graph, every two vertices, either they're adjacent or there is a unique path of two hops that connects. My path system is generally going to be those. If two vertices are adjacent, then the chosen path is the edge between them. For most pairs, if they're non-adjacent, then the unique two-hop path between them is the chosen path. But there are 5 exceptions. As you can see here, for example, my choice between how to go from 2 to 8 is to go from 2 to 1 to 6 to 8, etc. The blue one tells you how to go from 1 to 7, and so on and so forth. There are 5 exceptional pairs. So you see, if to go from 2 to 8, I could go via 3 in 2 hops, but no, I prefer to do it like this. It's very easy to check, and it takes exactly a second to realize that this is a consistent path system. You know, let's check it. Why? So is it true that going from 2 to 8, the section that goes from 2 to 6 is a chosen path? Yes, and so that's very easy to verify. So it's a consistent path system. And now what I'm claiming is that this is non-metrizable. So let me prove it. And this is an example, but really, this example is very typical. We will see such things, a lot of such things as we proceed. So suppose that this path system, this consistent path system that I described to you is metrical, which means there are positive weights that I associate to the edges, and these are the shortest paths. In particular, as we said, going from my choice of how to go from 2 to 8 was via 1 and 6. So that's how much it should have cost. But I also had the option of going from 2 to 3 to 8. That's another way of going to. So I wrote down a whole system expressing this, that my chosen paths are better than the obvious one. And when I add all these up, I find out that all the inner edges, 6, 8, and 7, 9, and 8, 10, and so on, they're all non-positive. So that's a contradiction. And in this contradiction, I proved to you that this consistent path system is non-metrizable. And the way we say it in short is that the Peterson graph is non-metrizable. We will, I hope, get back to this with a more refined version of this, but that will come back. So let me, this is, you know, if I wanted to write what we discovered in 3 sentences, here they are. and I'll say this in more in a fuller version later on. So materializability is rare. There are very few materializable graphs. Yet there is an infinite supply of them. What's called outerplanar graph. If you don't know the definition, everything will be said in full. And this is the moment just for general impression. There are infinitely many non-trivial examples of materializable graphs. And I don't think I will be able to have much time to say a lot about this, but this is an extremely interesting point, that materializability is in P, as we say in short. In other words, I give you a graph and I ask you, is it materializable? Does it have a consistent path system that doesn't come from edge length? This can be decided in polynomial-time. I will only say, since I don't believe I will have much time to elaborate on this, this is a good example that being in P and being really something that we understand are not necessarily the same thing. So I'm the first to admit that although we proved what we said here, I really don't understand this, but we will get further in this later on. Okay, so a path system, I think by now you already know, it's a collection of paths, one per each pair of vertices, and consistency means that a subpath of a chosen path is the chosen path between these two vertices. An equivalent thing, the equivalence is really not difficult, is a consistent tree system. A tree system is a collection of spanning trees, one rooted at every vertex. And consistency means that if the U to V path in the tree of U and the U to V path in the tree of V are identical. It's really not difficult to show that these two notions are equivalent. It's very easy to pass from a path system to a tree system and from a tree system to a path system. So since it's so simple, let me just say what's written here is something that you can prove to yourself in a few minutes. It's really very simple. So how do you move from path system to tree systems? What's the tree that's rooted at V? You take all the paths from other vertices into V, and they obviously, quite obviously, because of consistency, they form a tree. They don't create any cycle. So that's it. And given a tree system, what's the path system? You want to know what the path is from U to V. We said the path from U to V with the tree rooted at U and in the tree rooted at V are identical, and that's the UV path. And to show that these two things are really the same is not difficult to do. So there have these two different ways of looking at our basic construct. Now, there is a lot, the whole thing is really fascinating. It's obviously the case that we are only starting to scratch the ground here. So let me give you some sense of it. You can also speak about a consistent partial path system, right? I mean, I only give you paths that connect certain pairs of vertices. That's but I require consistency. So again, if X and Y reside on the U to V path, and there is also the U to V path is defined, and the X to Y path is defined, then it must be that subpath. So the definition is quite natural, but many surprises. For example, if you look at this example here, you will see that this is consistent. So the paths are those painted in color. It's consistent, that's very easy to verify. But I cannot now extend it to a UV path. Why? It's very easy to verify, but just to give you a sense, let's say I decide to go like this. Then walking from here to here, I should have gone like this and not like that. Okay, it's very easy to verify. So it's not necessarily always extended. But if you have a path system that defined completely on a subgraph, then that you can extend. Okay, another property which is very interesting and on which we still don't know enough, and I think it's extremely interesting, is this notion of neighborliness, which I only mentioned. I mean, the notion will come up later, so this is why I define it. We had it before, so it makes perfect sense to say that, you know, if there is an edge that you never use, throw it away and restrict yourself only to consistent path systems which are neighborly. So if UV is an edge, then the path from U to V is that edge. Okay. Good. So I think by now you understand these definitions. I don't think it's repeated here again, but it seems to me like we've done enough of it. Okay. And again, just because it's a new notion, perhaps it's a good idea to. So in order to be non-metrializable, it's enough that I show you one consistent path system that's non-metrializable. That makes a graph non-metrializable. And it's enough also to consider the two connected case, something a little like I spoke before about OS problem. Okay, so there is really, so I said I will give you 1.5 proof. So 1/2 proof I already gave you, which is when I proved to you that Peterson is non-metrializable. So this is not a difficult proof that I want to show you now. That's, I should say, the proofs in this paper are quite technical, and that's perhaps one of the nicer, you know, more appealing proofs in this paper. And the proof is that we prove that cycles are metrializable, actually strictly metrializable, but let's not worry about it. So this is, I want to describe, I will not do all the details, but just give you, I think, enough information so you can complete the proof to yourself. So let's just get, so in other words, what does this mean? This means if I give you a consistent path system on a cycle, it comes from edging. That's the meaning of this. So there are certain very simple examples, again, that we saw before. An odd cycle has a consistent path, has a natural one. The shortest, the mean number of hops is, of course, consistent and metric and so on and so forth. And what we're going to show is essentially, this is the crux of the matter, so we will see. So what does this look like as a tree system? Well, understand the tree system, if you want to understand, you know, if this is your graph and you're looking at just the natural, the basic odd cycle metric on this, the tree corresponding to the yellow vertex is comprised of all the edges except for the yellow one. The path from here to here is like this, the path from here to here is like that, and so on and so forth. So the remaining tree is everything but the yellow edge. And you do this forever, and this is the tree system, the natural, so to speak, tree system corresponding to another cycle. Okay, so, but we want to prove the theorem that every consistent path system on the cycle is metrical. Okay. So, but what I said before, so a path system, a consistent path system, a consistent tree system, when understood, is essentially the same thing. There are two different ways of looking at this. And since this is a tree and this is a cycle, and the spanning tree is just a cycle minus an edge, then to specify a consistent path system is the same as specifying a consistent tree system, which simply means I should tell you for every vertex which is the single edge that it doesn't use in its tree. Okay, this is what I need to show you. Okay, and we encode it with this color coding. Okay, and here you see. Okay, so that's the one basic thing, and the other thing is so in other words, a consistent path system on a cycle is the same thing as the mapping from vertices to edges. Again, every vertex tells you which edge does not participate in the tree corresponding rooted at this vertex in the consistent tree system that we're talking about. Okay, so here is a small definition. So we're talking about, so to talk about consistent path system is the same way as talking about maps from vertices to edges in the tree. And I call such a map crossing if for every two vertices, either their image is the same or U and its image separate V from its image. Okay, that's called crossing. And a lemma that's not difficult, I'm not going to prove it to you, but it's really not difficult at all, is that such a mapping corresponds to a consistent path system, if and only if it is crossing. So now we have an even better understanding of what we're doing now. And so a consistent path system on the cycle is the same as a consistent tree system, is the same as a crossing mapping from vertices to edges. Okay, we can do edge contraction. So we understand what it means to contract an edge. And I should have told you, okay. Okay, so let me perhaps, that's the important notion of this move, the notion of persistent edges. See this example, this is a 6-side. So we were not in the simple situation where the graph itself is already geodetic. And what happens here is, in this specific example, is that the mapping takes this vertex to this edge and this vertex to this edge. And then we say that we have a name for this. We say that this white edge is persistent. And the theorem that we prove, and that's how the whole thing goes, says that if you have a neighborly path system and you contract a persistent edge, then you still see a consistent path system. And eventually the final theorem says that if you have a neighborly path system and you contract all the persistent edges, then you wind up with just the standard or a standard odd cycle. So for example, in this example, so why are these two edges white? Because this and this and this point at the same edge. And why is this white? Because this arrows this and this arrows that. And if you contract them, then what you get is exactly this 5 cycle. And the way to get this as a metric is you put weight epsilon on all the white edges, and weight 1 on all the colored edges, and that's it. So if fill in all the details, this is not difficult. We've more or less proved the cycles are strictly bitwise. Okay, so let's understand a bit better this notion of virtualizability. So let me remind you or tell you, if you never saw this, the notion of topological minor. If a graph contains a subgraph which is isomorphic to a subdivision of H, we say that H is a topological minor of G. And a theorem that we prove says that the topological minor of a metrizable graph is metrizable. So the metrizable graphs are closed under taking topological minor. And now I want to read this in reverse. And in reverse, it says that if a graph contains a subdivision of non-metrizable graph, then it makes it non-metrizable. And I will not say much about the proof of this, but so even more common than the notion of topological minor is the notion of a minor. And the natural question to ask would be, is it true that metrizable graphs form a minor closed family? So the answer is no, and this is what you see here is an example that this guy is metrizable, but if you contract this edge and you get this as a minor, then this is non-metrizable. So the situation is more complicated. However, this being closed under topological minor really gives us something very interesting. So let me dwell on this for 2 minutes because this is interesting. This is, I think, atypical. And what I want to stress here, which is very important. So I'm a great believer in using computers in research in combinatorics. You can do these things wisely and less wisely. So we try to do this wisely. And I think this is a very good example of success of this. So Daniel found, we call this the zoo, this set of 10 graphs improved that all of them are non-metrizable. How did he find them? By computer search. And how did he prove that they're non-metrizable? He constructed a consistent path system for each one of them. And then what he did is, in the same way that I proved to you before, that Peter said is non-metrizable because that path system leads you to a contradiction. In each one of these cases, he was able to do the same and prove. Now, the nice thing is that I don't believe, or I doubt that we would be able to find these 10 graphs if we worked by hand alone. We really needed the computer for this. However, the proof that all those are non-metrizable is something that the human can easily verify. It's just a system of linear inequalities. You add them up and you conclude that so this is really a crucial step in our proof. And I doubt that it could have been done without using a computer, without Daniel's, so not only as an excellent mathematician, but also a terrific programmer. And so now we have two alternative ways of proving non-metrizability. Either you explicitly construct a path system, and like we did with Peterson, or you find a subdivision of a non-metrizable graph from the zoo. And in particular, this shows, I will not dwell on this, that you could, for example, this way provides an alternative way of showing that Peterson is non-metrizable. But this really now gives us a very powerful theorem with the effect that metrizability is rare. So let me read this theorem aloud. If a two-connected graph has 8 vertices or more, and it contains a subdivision of a 3-connected graph other than K4, W5, and K5 minus D, and then it's non-metrizable. But getting this more directly down to earth, every 3-connected graph with 8 vertices or more is non-metrizable. Every 2-connected non-planar graph with 8 vertices or more is non-metrizable. Every 2-connected graph with minimum degree at least 3 and at least 13 vertices is non-metrizable. So it's really very, I mean, almost every graph in a very, very strong sense is non-metrizable. What is much harder, and I already see I'm going to run into trouble with time, is to prove metrizability. We saw it in one example. We saw that cycles are metrizable. So I will not say much more about this. We have this notion of a suspended path and being able to add a suspended path. But the outcome of this is this theorem, that an outerplanar graph, or every outerplanar graph is strictly metrizable. So this is much more general than cycles. Cycles are outerplanar. What does the outerplanar mean? It's a graph that can be drawn in the plane in such a way that all the vertices are on the outer face. And it's you could see the cycle proof was, if you want, an exercise that prepared us for this. We still don't know, but really, let me dwell on this because I think this is of greater importance than just one more result like this or like that. While we do have a very efficient way of proving that the graph is non-metrizable, namely we write either by finding one of the graphs in the zoo or by giving, and we know that this is quite general, that we can write a linear program which is infeasible and this way prove that the graph is non-metrizable. We still don't have any good general method to prove that a graph is metrizable. We sweat quite hard to prove that outerplanar graphs are non-metrizable, are metrizable, sorry. but in general, this is still very mysterious. So a key ingredient in the proof of being polynomial-time decidable is so there is. This is one of the greatest achievements of combinatorics is the Robertson-Seymour forbidden minor theorem, which says that every minor closed family, minor closed, is characterized by a finite set of forbidden minors. There is no such thing as these graphs show you. There is no such thing for topological minors, and yet using another. So it's much easier. We didn't have to go into the depth and the difficulties of Robertson and Seymour. We managed to show that the class of metrizable graph is characterized by a finite list of forbidden topological minors. We don't know what this list is. And so this shows you that this is only an in principle proof of being in P, but we really don't know how to do it. So this is still very, very interesting subject to. Okay, let me, I think I have, am I right? I have another 4 minutes. So let me quickly tell you about another result that Daniel and I have proved. You see, what happened in the first example that I showed you, the Peterson, is that this path system was reducible. If you think of the outside vertices as black and the inside vertices as white, and you spend a minute thinking about this, it's really made up of two atoms. This molecule is made up of 2 atoms. You never really have to go between black and white, back and forth. So it's really, this is a reduction. And we're asking ourselves whether there exists also, as we saw, there are not only other lots of non-metrical, most graphs of non-metrizable, we asked ourselves if there is one which is irreducible. So we're able to show that the Paley graph, which I'll define in a second, the Paley graph has a path system which is irreducible. So what's the Paley graph? This is one of the wonderful constructions that from number theory that combinatorialists like a lot. The Paley graph, you take a prime P, which is 1 mod 4. So -1, -1 is a square. And you create a graph whose vertices are all the elements of the finite field of order P. And you connect 2 vertices by an edge if their difference is a quadratic residue. This has lots of wonderful properties. I will not go into this, but if you never saw this, that's something that you really want to get acquainted with. And we found the following path system, which is consistent and irreducible. There's still a lot to do here. As I said in the beginning, we don't even understand the metrical one, what these look like, which graphs has lots of metrical path systems. There is still so much to do here. So yeah, this shows how to prove to yourself that a certain graph is non-metrizable. And with that, I think I will stop. Thank you.
Thank you. Are there any questions? So you mentioned this forbidden topological minors, right?
Right. Right.
So does it matter when you define metrizable or strictly metrizable? So you have 2 concepts, right?
No, strict metrizability just means that the inequality, I mean, it's an interesting distinction. The inequalities are sharp, that's all. So do you allow also the equalities or not? So it's let me put it this way. So far we didn't find any very substantial differences between metrizability and strict metrizability. They are 2 At the moment, our theory still doesn't really distinguish between them. What is still very interesting, and unfortunately we don't know enough about this, I think there is a lot still waiting to be done, is the neighborly case. In hindsight, I think this is the more natural concept, and we are returning to this. This is definitely something about which we still don't know enough. Understanding neighborly consistent path systems. So you always use, when there is an edge, you always use. This is somehow, seems to me, the more natural object, but we still know too little about this.
Well, Nati, I have a question about the definition of this path system. So
Yes.
I can kind of understand the second requirement that the subpath also belong to the system. Why we insist on having a unique path in the system between 2 points? Is there?
Without a unique path, I don't even know how to get started. No, I'm not saying that there is, I mean, I don't see, do you have any suggested concept that would be interesting and rich? Let me say this right away. You know, understanding the metric of graphs is a huge, completely poorly explored territory. So I wouldn't be surprised at all if you have a suggestion. For example, I mentioned this. Even questions like, you see, I give you 2 weight systems on the edges of a graph. They both define a path system. And I want to ignore now ties. It's really not important for my discussion. So let's say my weights are algebraically independent. Doesn't matter. I mean, they're generic, okay? And I say that 2 such assignments are equivalent if they define the same shortest path system. I mean, which graphs have lots of such, how large can it be? Even very basic questions like this, we still don't know. So there is a lot to be done here. You know, you really want to think of a graph as a geometric object. This is an important, very important concept. And in certain ways, we know things about it, but there is so much that we still don't know. So this is where we're headed.
So I guess you don't have any upper bound on the size. So you don't have any upper bound on the size of a forbidden topological minus.
No. That's, you know, that's a part of the theorem, you know, which I can write as a mathematician. It's a finite list, but as a human being, I'm telling you, I have no idea at all. There remains a lot to be understood. Even further than that, you know, I know that I can in polynomial-time decide materializability, but it's ridiculous how little we understand it. So there is really so many basic things that really still have to be done.
Any other questions?
Maybe I missed the point. I wonder, is there any common property between the graphs of the zoo you presented before?
No. Just the only property is that they are small. They're small enough so that Daniel could analyze them on the computer. That's all.
Okay, thank you.
For each one, we have a short, humanly verifiable proof that they are non-materializable. And then essentially what the proof does is it shows you that for most graphs, you will find one of them as a topological minor. You know, if I really want to tell you the whole proof in 2 sentences, that's how the proof goes. We found these 10 on the computer. We wrote down proofs that humans can easily verify. And then we work hard showing that essentially, you know, if you take any non-trivial graph, you know, a graph with non-planar large enough, you'll find one of them as a topological. This is essentially how the proof goes.
Okay, thank you so much.
there's no further questions, then let's thank the speaker again.